Hello everyone. In this lesson, we will continue to study the frequency domain analysis model of continuous system. Today, we will study signal sampling. The main contents include the concept of signal sampling, impulse sampling, which is also called ideal sampling, and for rectangular pulse sampling, we mainly discuss the principle of signal sampling and its time domain characteristic and a frequency domain characteristic. First, let's take a look at the concept of sampling. Continuous signal sampling is a bridge for the conversion of a continuous signal to a discrete signal, and it is the first link for digital processing of signals. Figure 1 is a schematic diagram of signal sampling and recovery. Ft is a continuous signal. Pt is a sampled signal. When Ft and Pt are input to the multiplier, the sampling signal Fst is obtained. After quantitating and coding sampled signal, we can get its digital signal Fk. After performing corresponding digital filtering on this digital signal, we can get the output Gk. When we perform DA conversion or digital to analog conversion on it, we can get a continuous signal Gt. This is the schematic diagram of signal sampling and recovery. Generally, the sampling pulse here is a periodic signal. It can be the ideal shock sampling that will be discussed later, or it can also be a rectangular pulse sampling. To discuss signal sampling, we should solve the following questions. First, what is the relationship between the spectrum Fj omega of the sampling signal Fst and the spectrum Fj omega of the original signal Ft? Second, what method should be used to recover the original signal Ft from the sampled signal? Let's look at the ideal sampling. Ideal sampling means that its sampling pulse is delta Tst, which is a periodic unit impulse sequence. It is assumed that Ft is a band-limited signal. Its highest frequency is omega n. The spectrum of the sampled signal is Fsj omega, and its unit impulse sequence is expanded to Fourier series in the exponential form. If we take the Fourier transform, we can get its corresponding spectrum. We have learned that the spectral characteristic of the impulse sequence is still an impulse train. The intensity is omega s. In this way, according to the principle of signal sampling, the sample signal Fst is equal to Ft times delta Tst. We have learned that according to the frequency domain convolution theorem, the product in time domain equals the convolution in frequency domain. Then we can get the spectrum of the sample signal Fs is shown in Formula 1. In this calculation, we use such a basic expression. Omega s over 2 pi equals 1 over Ts, according to the frequency domain convolution theorem. There is a coefficient 1 over 2 pi in this formula. In the expression of the frequency spectrum of the original impulse signal, there is a coefficient omega s. So according to omega s over 2 pi equals 1 over Ts, we can get expression of Fsj omega, as shown in Formula 1. From Formula 1, we can find that the spectrum of the sample signal is related to the spectrum of the original signal. There is a corresponding spectrum shift. The spectrum shift occurs at n omega s. Omega s is the sampling frequency of the sampling pulse, and there is a coefficient 1 over Ts. Let's take a look at their time domain waveforms and frequency domain waveforms. In the time domain, after the signal Ft is multiplied by the sampling pulse, we can get a waveform of its sampled signal fst in the time domain. The product in time domain corresponds to the convolution in frequency domain. Suppose this is the spectrum of the original signal. This is the spectrum of the impulse sequence. After convolution, the obtained fsj omega is the spectrum of the sampled signal. Obviously, here we can find that the spectrum of the sampled signal is obtained after corresponding period extension of the spectrum of the input signal. Its period is omega s, and the amplitude of fj omega is 1 over Ts. By observing the spectral characteristic of the sample signal, we can find that in Formula 1, when n is equal to 0, obviously the spectrum of the sample signal fsj omega is equal to 1 over Ts times fj omega, which means that in the first period from minus omega m to omega m, the spectral fsj omega of the sample signal is equal to 1 over Ts times the spectrum of the original signal fj omega. It contains all the information of the original signal. Here, Fs is a continuous spectrum with a period of omega s. If you connect an ideal low-pass filter, its gain is Ts. If its cutoff frequency is omega c, as long as omega c is greater than omega m and less than omega s minus omega m, its high-frequency components can be filtered out to recover the original signal spectrum. Here you should note the frequency of this point. Actually, the frequency value of this point is omega s minus omega m, because the spectrum is shifted according to omega s. This is the bandwidth of the original signal. Therefore, it is required that omega c is greater than omega m and less than omega s minus omega m. The frequency at this point is very critical. The frequency at this point is determined by omega s. Therefore, omega s minus omega m must be greater than omega m. Otherwise, the spectrum of this point will overlap with that of the original signal. Therefore, omega s must be greater than 2 omega m. Otherwise, it will cause spectrum aliasing through analysis of the ideal sample signal. We should know that, first, only when omega s is greater than 2 omega m, there is no spectrum aliasing after shifting. That is to say, the sampling frequency cannot be too small. In addition, in the case that omega s is greater than 2 omega m, if you want to recover the original signal, you need a low-pass filter. The bandwidth of this low-pass filter, omega c, is greater than omega m and less than omega s minus omega m. Let's look at an example of spectrum aliasing. If the spectrum of the original signal is like this, when it is ideally sampled, there is no frequency aliasing. The spectrum of the sample signal is shown in Figure A. However, once omega s is less than 2 omega, spectrum aliasing may occur, as shown in Figure B. Obviously, its spectrum is not the same as Figure A. Here the spectrum obviously overlaps. For the spectrum with aliasing, it's difficult to recover its original signal with a low-pass filter. These waveforms can be simulated by software. Let's look at rectangular pulse sampling. The subject of rectangular pulse sampling is a rectangular pulse. This is the original signal. This is the sampling pulse. After ft is multiplied by pt, we can get the time domain waveform of the sample signal. Obviously, the width of the sampling pulse determines the accuracy of the sampling value. According to the same analysis method, the sampling signal is multiplied in time domain and convolved in frequency domain. Since the subject of sampling is rectangular pulse, so the smaller the value of tau, the more accurate the value of discrete time. However, in signal transmission, we should notice whether the sample signal includes all the information of ft. In this way, the spectrum structure of the sample signal must be considered. In fact, in order to ensure that the spectrum does not alias after sampling, the continuous system should be a band-limited signal. Let's take a look at the spectrum of the rectangular pulse sampling. This is the product in time domain, and this is the convolution in frequency domain. The spectrum of rectangular pulse signal conforms to Formula 3. Because the rectangular pulse is also a periodic signal, its frequency spectrum will change in the form of an impulse function. Pn is its coefficient. Its spectral coefficient changes according to Formula 4. That is to say, it changes according to the law of sampled signal. Obviously, Formula 5 is the spectrum of the rectangular pulse. Through the convolution, we can get the Formula 6. Make a simple comparison between Formula 6 and the Formula 1. It's obvious that the spectrum of rectangular pulse sampling is shifted. However, this is not a simple period extension, because after it is shifted, its spectral coefficient changes according to the law of sampled signal. Therefore, the spectrum analysis of rectangular pulse and impulse sampling have certain difference. Let's look at its sampling process and its spectrum. In time domain, after continuous signal ft is multiplied by rectangular pulse pt, we can get fst. In frequency domain, the spectra of the original signal and the spectrum of the rectangular pulse are convolved. We can get the spectrum of Fs. Next, let's discuss the influence of the width tau of the rectangular pulse on the sampled signal. For rectangular pulse sampling, as long as omega s is unchanged, or its period Ts is unchanged, its position will not change when the corresponding spectrum is shifted. However, since tau has an influence on the spectrum of a rectangular pulse, 2 pi over tau is the first zero crossing point, so if the width of the rectangular pulse tau gradually decreases, its first zero crossing point will be far from the origin. That is to say, the occupied bandwidth will be wider. So, for a rectangular pulse, when its pulse width tau approaches zero, it approaches delta t. In this lecture, we mainly discussed the concept of signal sampling, impulse sampling, and rectangular pulse sampling. Through analysis, we can find that impulse sampling is an ideal sampling. Rectangular pulse sampling is a sampling method commonly used in actual engineering. When the width of the rectangular pulse tau approaches zero, the sampling of the rectangular pulse will be approximate to the impulse sampling. So much for today. Thanks for your listening. Goodbye.